Hello, Doug Littrell again. This is November 6, 2019. I have a presentation. It'll probably take about a half hour. It's on surface gravity ciphered from 3 Telluric planets, Mercury, Venus, and Earth. I put this in an outline so that I don't miss anything. If I speak off the cuff or extemporaneously, sometimes it doesn't come out as well. So I'm trying this. This video will show how to digest some key facts about a surface gravity gradient that emerges between 3 Telluric planets in our solar system, which I believe will lead to an orbit standardization equation that discredits every relativistic concept rooted in the equivalence principle. Roman numeral number 1. The equivalence principle contrasted between this pair of Newtonian type equations. One of them is a Newtonian equation. It's a well-accepted one. Anyway, A, 3, the equivalence principle posits all things falling at the same rate regardless of mass. B, this appears to be based not only on some experiments by Galileo, but also how the orbit velocities of planets in this solar system seem to be detached from their M2 masses. Now what an M2 mass is, you'll pick that up as I go on. You should. C, both a body's orbit velocity as well as its gravitational force that is reciprocated between its mass and the primary body it orbits can be found using a common equation credited to Isaac Newton, even though one of its elements was added after the Cavendish experiment was conducted a year or so before 1800 by Henry Cavendish. That resulted in the gravitational constant that became part of the equation, even as Newton lived about a century before Mr. Cavendish. Still, it was Newton's conception of gravity that ended up guiding this now well-accepted equation for establishing a value for gravitational force, which equation can also be mathematically rearranged to assign orbital velocities for the planets in this solar system, wherein the M2 mass can be cancelled from the equation as if the M1 mass, i.e. the mass of the Sun, decides all without any effect from the mass of the M2 body on that velocity. That equation, that Newtonian equation, is as follows. F, as in gravitational force, equals the gravitational constant times M1 in parentheses times gravitational constant times M2 in parentheses, that's the way I write it, divided by the orbital radius squared, which is simply the mean distance between the two bodies. That equation is as follows. Well, I've got that. Recently, I have begun to use this equation to assign the gravitational force in newtons that is exerted and reciprocated between several of these planets during conjunctions, which I contend that over the course of billions of years has brought some of their velocities down from what those would be if they were the sole secondary body orbiting a star like the Sun in a separate solar system. At each one's current distances, with no other large bodies present to have an effect on them, which is what an orbit standardization equation that I'm attempting to find should eventually express, hopefully sooner than later, in terms of any secondary's orbital velocity relative to its mass having significant influence on that within such a setting. In my new book, For the Sake of Civility, that just came into print and was delivered last month, such an equation was offered which made the orbit of Venus at both that planet's respective distance from the Sun along with its mass, the baseline, the orbital elements or proportions that Venus has. The baseline for that kind of standardization relative to orbital velocity, which equation was then applied to all of the significant moons in this solar system to see if their orbital element proportions varied from that kind of touchstone. That equation still appears to work well for realizing differences in orbital velocities of moons orbiting at certain distances from Jupiter's center of mass when comparing to those velocities of moons that orbit Saturn per each one's mass and distance from Saturn's center of mass, for example. However, a new quest for a better orbit standardization equation is now on, since a body's orbital circumference, that is, a rough estimate of the length of one's trek during a moon's full period, a complete orbit, was placed above the line of division in the equation, being multiplied by the number of newtons involved, with the newtons found using the other main equation just given for each involved body's mass and distance affecting its gravitational force and orbital velocity, which, using the orbital circumference in such a manner, would at extended distances skew the results the more pronounced those distances become. That's why I'm looking for another one. Still, that equation seemed to work well, just the same, for comparing the orbital velocities per distances and masses of all those moons, all of which are relatively close to the primaries, which was meant to express how much such orbits varied from Venus's orbital proportions relative to the Sun per its mass and distance. That equation was, in that book, it appears as V, the orbit, that is the orbital velocity, equals the cube root of n newtons, the newtons found by the other equation, times capital C, once again, with n being the number of newtons per each one's mass and distance using the first equation, while C, the capital C, was the orbital circumference, which is once again a rough estimation of the amount of distance traveled during a complete period. Then to divide that by the cube root at just over the whole number 3, this time at a cube root of 3.075, that specific value for the cube root applied to r, the orbital radius again, or the distance between the primary's center of mass and that secondary body. Now, the orbital radius, r, a small r, is below the line of division that expresses division. It's not squared like in the first one, it's just r, but it's the cube root of that. And what that did, that gave us Venus's orbital elements, its proportions in relation to the Sun. That's all that did. Roman numeral number 2. An explanation of what a Newton is relative to both gravitational force and orbits. A. 1 Newton is an SI unit of measure for assigning the force required to push a 1 kilogram object 1 meter within the span of 1 second, where an acceleration is implied, since that equation is A, as in acceleration, equals 1 meter per second squared. B. But I would like for you to now think of newtons in 3 ways instead of just 1, meaning not just what causes acceleration. For newtons can quantify 3 different kinds of forces, with one being momentary push force, which is the force exerted for an instant, then it stops, which is done within a fraction of a second typically. During a collision, which tends to result in some acceleration of one of the objects when 2 bodies are involved, along with some recoil in the other, as seen when a bat hits a baseball. Secondly, newtons can also quantify continual push force. This is continual push force. as in the case of a 1-pound sphere sitting on a table near Earth's surface as it experiences Earth's 9.8 meters per second of surface gravity. This can be converted to pounds like those read when using a spring scale that anyone can stand on to weigh him or herself, even as 1 pound, that 1-pound sphere exerts 4.448 newtons of continual push force on such a table. That can then be converted into 1 newton, equaling a little more than 1/4 of a pound of continual push force. Thirdly, newtons can be used to quantify continual pull force as well, which is what occurs in orbits. Therefore, imagine a strap placed around 2 objects that have some resistance to each being drawn closer by such a strap, being incrementally shortened with something like a motor-driven winch that can reel up that strap in small amounts moment by moment in order to draw such objects closer together. That is, if the resistance force keeping them apart isn't too much for the limits of the strap and winch. C. This is how gravity relative to orbiting bodies works, even as it is the force of attraction reciprocated between 2 celestial bodies, which can be expressed in newtons of attraction force that is pulling between 2 such bodies. Thus not warp space, nor any fabric or structure in space caused by gravity next to such bodies, serving to corral such bodies into circular type tracks around the much larger body of the 2. D. The resistance to gravity that in a sense is the reeling in of an object toward it, i.e. reeled in like when an object falls straight down toward the surface of a major gravity source like Earth, but including the Sun as well. Now, there's of course acceleration per second. It accelerates by a certain rate per second. That's what that surface gravity, it's a G-force, is quantifying. It's acceleration when things are dropped. They don't just keep going the same rate, they accelerate in any surface gravity, whether it's a slower one or one of the quicker ones. Anyway, when it's reeled like when an object falls straight down toward the surface of a major gravity source like Earth, but including the Sun as well, that resistance force is momentum in the case of orbits, which needs to be viewed as more distinct from simple inertia when it comes to orbits. For when driving a car at, say, some 50 or 60 miles per hour, and the steering wheel is turned somewhat abruptly, momentum is what causes any passengers that are free or unattached to the car's frame to appear to move in the opposite direction from which the car has been turned, which body or bodies are actually trying to continue straight ahead. That is the phenomenon of momentum expressing itself as trying to force an object that's already heading in a given direction. It exerts some force for it to continue on ahead in that direction, i.e. G-force, as it's also called, which applies to orbits also, not just turned objects on Earth's surface. Next, with regard to momentum, is how when the driver of the car steps on the brake pedal too abruptly, the passengers will be thrust forward, even toward the car's windshield, ultimately in severe cases. In that case, momentum is trying to force a body and or object that's detached enough from the car's frame to continue ahead at the same velocity. So momentum is trying to keep an object that's moving headed in the same direction as well as at the same velocity. This is what is occurring in orbits. In the orbits of the 8 planets here, each one's entire body is being attracted to the Sun, which isn't analogous to a car that turns, but everything inside the car as well, which isn't only analogous to a car that turns, but everything inside the car as well that is being held in place. And on a planet firmly as well as evenly, including rigidly to some extent, to the car's frame by the body's surface gravity. So there's an analogy there. So gravity from the sun collaborating with such a secondary body's gravity is analogous to the car's steering wheel being turned. But when it comes to a car's brakes, there are generally no brakes in orbits, though collisions can at least make some kind of attempt to complete a full stop. Which happens, of course, when a smaller object in space hits a moon or a planet and it does stop. So that does happen a lot, but a lot of time there isn't a complete stop as well. Yet an even better analogy is a strap, once again trying to reel in a secondary body that it has attempted to fly by the sun. If the body is headed too much toward the sun, it will be turned by gravity enough so that it collides with the star. If the body coalesces next to the sun, if it has coalesced next to the sun and had enough distance from that star where it coalesced, then when it gains enough mass, while material is also being added to both it and the sun, it must spiral in instead of heading straight toward the sun, even as all of that gas and dust must take each segment's turn at reaching the sun, which imparts sideways momentum in a direction that heads off toward one side of the sun. But as it accrues more mass, the body next to this out from the sun that's coalescing, it will begin to fall more toward the sun as it gains more mass, so that its compromised direction caused by the pull of gravity and momentum attempts to keep it headed just off to the side of the sun. So its increased velocity, coupled with the sun's attraction to the sun's side of its path, still attempts to turn it so that it might intersect. Nevertheless, its increased velocity during that body's somewhat angular fall will end up taking it on past the sun by that extra velocity it's gaining that it accrues while falling, i.e. velocity toward the most pronounced direction that isn't directly at the sun, which grants it even more momentum in its slowly changing direction to make the body want to fly off on past the sun. Yet the farther away its additional velocity that is accrued takes it out from the sun on its other side, that will lead to it being slowed by the sun from behind, now from more behind it, pulling on it again, now from somewhat behind the direction it's heading, which results in the body turning back more toward the sun once again, which will eventually lead more or less to somewhat of a circular orbit that should even out its most erratic aspects as well as lessen some of its original eccentricity as time moves on, i.e. the true dynamics of orbits, all of that. Roman numeral number 3. Now on to describing that surface gravity gradient. A. Surface gravity is customarily expressed in terms of how fast a falling body accelerates near the surface of a large body like the Earth. On Earth, that value is 9.8 meters per second squared. On Mercury, it's 3.7 meters per second squared. On Venus, 8.87 meters per second squared. On Mars, 3.72 meters per second squared. Meanwhile, there is a surface gravity gradient that can be derived from known and or directly measured surface gravity values of not just Earth, but of Venus and Mercury also, when compared as their masses affect those. Mars, whose mass is very near to being double that of Mercury, must be initially disqualified for use in finding this surface gravity gradient, since its mean density is too low, which serves to skew its surface gravity relative to its volume compared to a body of the same volume having a density that's more similar to Earth's, including Mercury's and Venus's. Furthermore, Earth's mean density is 5.514 grams per cubic centimeter. Mercury's 5.427 grams per cubic centimeter. Venus's 5.243 grams per cubic centimeter. Whereas Mars is much lower at 3.9335 grams per cubic centimeter. Even so, lower density always lowers surface gravity, which has for many decades been measured over Earth's surface with gravimeters. With a gravimeter being a weight suspended by a sensitive spring, having a pointer next to a calibrated scale to its side, used in order to locate the vicinity of something like an oil field below Earth's surface, since oil has a much lower density than Earth's most typical forms of solid rock. B. One of the factors that can skew surface gravity is centrifugal force when exerted, much as a centrifuge from a fast spinning planet's equator, which occurs on Earth but not on Mercury, since it makes one complete revolution in about 58 days. Please compare that to its 88-day period. Whereas Venus, with its approximately 224-day period, is tidally locked so that the same side of its surface always faces the Sun to give it one full revolution per each completed period. Therefore, centrifugal force slinging bodies outward a small amount at Earth's surface causes objects to weigh less at the equator than at one of its poles. Yet Mercury and Venus both lack that feature. Still on Earth, however, most any skewing of surface gravity such as that is generally so minute, typically at only around 0.5%, whether due to a small density variation or a centrifugal force, prevents those factors from precluding a surface gravity gradient like this from being established. C. The next step in this is to begin approximating the surface gravity of similarly dense imaginary Telluric planet of, say, 1 septillion kilograms, which would be roughly 3 times Mercury's mass, i.e. assigning it a surface gravity of roughly 4 meters per second squared compared to Mercury's 3.7 meters per second squared. So after that, let's try adding 1.2 meters per second squared of surface gravity for every 1 septillion kilogram of added mass to a hypothetical planet. So once again, 1 septillion kilograms would have a 4 meter per second surface gravity. Then with the kind of density that Mercury, Venus, and Earth have in that range. Then at 2 septillion kilograms, there would be a surface gravity of 5.2 meters per second per this kind of gradients increase. Then at 3 septillion kilograms, it would have a surface gravity of 6.4 meters per second. And at 4 septillion kilograms, there would be a surface gravity of 7.6 meters per second squared. Then on to 5 septillion kilograms, which is very close to Venus's mass at 4.867 septillion kilograms. There would be a net surface gravity of 8.8 if you kept the gradient going, which is very close to what has been measured on Venus. Now, it didn't fall right on Venus's mass, but it fell at 5 septillion kilograms, which is close. Next, add 1.2 meters per second squared of surface gravity as 1 more septillion kilograms is added to that, which brings the total mass up to 6 septillion kilograms, which ought to yield a 10 meter per second squared surface gravity. Even so, Earth is indeed nearly 6 septillion kilograms at 5.972 septillion kilograms. Yet, as a certain amount of mass has been successively added to these overall bodies, this surface gravity gradient, whose steps are evident when comparing these three Telluric planets, its increase begins to tail off from continuing to add 1.2 meters per second of surface gravity for each additional septillion kilograms of mass added, as it now drops to less than 1.2 meters per second squared per a 1 septillion step up in mass. Therefore, in bodies with 6 and over septillion kilograms of mass, the step up is likely very close to 1 meters per second squared of added surface gravity, making 11 meters per second squared at the 7 septillion kilogram level a very good estimation, and so on. I would explain why that's happening. I've touched on that in my new book, but I want to limit the length of this video. D, this is borne out, I'm almost finished. This is borne out in the gravity intensification explanation found in the book for the sake of civility that shows the orbits of moons around planets with less dense, and this relates to what I was just going to say, but it's not the full picture. That shows the orbits of moons around planets with less dense extremities, how that adds lots of extra distance essentially from one center of mass due to low density materials residing high up and away from its much denser deep interior. This imparts slower orbital velocities to such a planet's moons per their masses and distances when compared to moons that orbit over a planet with more density in its extremity. Much as how the highest much as how the higher density ices of Saturn reach farther out from its center of mass compared to Jupiter's less dense gases residing there, which ends up lowering Jupiter's moons' orbital velocities per their distances to its center of mass at comparable distance from Saturn's center of mass when using an equation that can express those differences, which I developed one. It's just not perfect. E, all of this means, for one thing, that surface gravity amounts can be assigned to any planet mathematically based on that gradient of increase continuing, although lessening, at the same rate as larger and larger mass planets are included. Yet where such a body's surface gravity might start, as in where its surface might start, by use of that method will likely not place it where one's rocky or dense metal surface meets its thick gases or ices, or in the case of ice giants where their outermost ice meets its thick gas envelope, as with Saturn, and also Neptune and Uranus. Once again, surface gravity amounts as how those, this is the conclusion, once again, surface gravity amounts as how those increase per increased body mass that is now on display here discredits the equivalence principle, which is a key conceptual fundamental undergirding all that relativity stands for, inasmuch as varying mass bodies with enough mass contrast do exert varying amounts of the attraction force of gravity out across space toward other objects and bodies, which changes both the acceleration rates of those objects that are near enough to fall toward them, also the amount of push force pressed down upon their surfaces by bodies or objects setting upon them.